to Unit 6. We've spent the first 5 units building analytical tools: probability, testing, measurement, causation, and study design. Now we zoom out to the population level. This unit is about how disease moves through groups of animals, how we define those groups, describe their disease patterns, understand transmission dynamics, model spread, and design control programs. We start at the very foundation, the epidemiological concept of a population, and the descriptive tools we use to characterize disease within it. These may seem basic, but precision here is fundamental. You cannot measure disease in a population you haven't defined, and you cannot interpret disease patterns without the who, where, and when framework. This talk is shorter than most because the concepts are foundational and will be built on heavily in subsequent talks. Let's build them carefully. The epidemiological concept of a population is more precise than the everyday use of the word. In epidemiology, a population must be defined along 3 dimensions: animal, place, and time. Without all 3, you don't have a well-defined population. And without a well-defined population, your prevalence and incidence estimates don't have a denominator, which means they're not rates at all, just counts. Animal, who is included? Species is the obvious starting point, but breed, age, sex, production purpose, and health status all matter. A study of respiratory disease in recently weaned stocker calves is a very different population from a study of respiratory disease in mature beef cows, even on the same farm. Pooling them would obscure the age-specific dynamics of the disease. Place. Where is the population located? Geographic boundaries matter both for defining exposure and for understanding context. Disease patterns differ between regions because pathogen environments, climate, management practices, and biosecurity infrastructure differ. A study of mastitis in the upper Midwest dairy belt may not apply to operations in the arid Southwest. Time. When is the population being studied? This is particularly important for disease with seasonal patterns, for outbreak investigations with a defined time window, and for longitudinal studies where population composition changes over time. Cattle in this feedlot means very different things in September than in March. The animals may be entirely different. Descriptive epidemiology is the first step in every disease investigation, from a herd-level mastitis problem to a regional outbreak of a reportable pathogen to a global pandemic. Before you ask why, you need to know what, who, where, and when. Descriptive epidemiology answers those questions. The person, or in veterinary medicine, the animal, dimension tells you which subgroups are most affected. Is disease clustered in one age group, one sex, one production class, one pen? These patterns generate hypotheses about risk factors. If all the sick animals are from one pen, the pen is a unit of analysis. If all sick animals share a water source, water is a hypothesis. The place dimension reveals spatial patterns. Is disease distributed uniformly across the operation, or is it clustered in specific locations? Spatial clustering around a specific source, a water trough, a feed delivery point, a shared airspace, strongly suggest environmental exposure. Uniform distribution suggests systemic or management level exposure. The time dimension is captured in the epidemic curve, a histogram of cases over time. The shape of the epidemic curve is one of the most powerful descriptive tools in outbreak investigation. A sharp peak with a narrow time window suggests a point source exposure. All animals were exposed at roughly the same time to the same source. A prolonged, gradually rising and falling curve suggests continuous exposure. A series of waves suggest propagated spread from animal to animal. We'll build epidemic curves fully in Unit 7, Talk 7.2. Descriptive epidemiology generates hypotheses. It does not test them. The pattern of who, where, and when gives you specific testable ideas about exposure sources and risk factors that you Then pursue with analytical studies, case control, cohort, or outbreak investigation. Descriptive statistics are the numerical tools we use to summarize the distribution of disease and its determinants in a population. They're the numbers that fill in the picture painted by descriptive epidemiology. The first choice is always between measures of central tendency. Where is the middle of the distribution? The mean is the arithmetic average, intuitive and widely understood, but sensitive to outliers and skewness. If one animal has an extreme value, it can pull the mean substantially. The median is the middle value when all observations are ordered. It's robust to outliers and is a preferred summary for distributions that are skewed. The mode is the most common value, rarely the most informative for continuous data, but useful for categorical variables. The second choice is a measure of spread. How variable is the distribution? The range, minimum to maximum, is simple but strongly influenced by extreme values. The interquartile range, the range of the middle 50% of values, is more robust. The standard deviation measures average distance from the mean. Meaningful and mathematically elegant for normally distributed data, but can be misleading for skewed distributions. The practical rule is match your summary to the shape of your data. For normally distributed continuous variables, body weight, blood glucose in a healthy population, report mean and standard deviation. For skewed distributions or ordinal data, days in milk at culling, body condition scores, pain scores, report median and interquartile range. For categorical data, disease present, absent, treatment group, breed, report counts and proportions. This connects directly to the statistical literacy concept from Talk 3.4. Using the wrong summary statistic isn't just aesthetically wrong, it misrepresents the data and can lead readers to incorrect conclusions about the central tendency and variability of the population you're describing. Let's put descriptive epidemiology to work with a brief example. We have a respiratory outbreak in a 1,200 head wean to finish pig barn in the Midwest in February. Animal: pigs 6 to 10 weeks of age, recently moved from nursery to grow finish. This age group is immunologically vulnerable. Maternal immunity is waning and their own immune systems are still developing. Place: cases are clustered in 2 rooms on the east side of the barn, the rooms closest to the intake ventilation system. The spatial pattern immediately generates a hypothesis. Something about the air coming in through those vents is driving disease. Cold incoming air, high humidity, poor air mixing, all are plausible mechanism. Time: cases began 5 days after a cold snap forced the barn management system to reduce ventilation rates to maintain temperature and peaked at day 9. The epidemic curve shape, gradual rise, peak, gradual decline, is consistent with either continuous exposure or propagated spread rather than a point source. The 5-day lag after ventilation reduction is consistent with an incubation period for viral respiratory pathogens. Descriptive statistics: 142 cases out of 1,200 pigs, attack rate of 11.8%, mean age at onset 7.3 weeks, with a tight standard deviation suggesting age-specific susceptibility is real. Median severity score of 3 on a clinical scale, giving the vet and producer a sense of the clinical burden. Hypothesis: reduced ventilation, accumulated pathogen, cold stress suppressed immunity, east rooms receive particularly cold or humid air. These are specific testable hypotheses. The next step is an analytical study, perhaps a cohort comparison of east side versus west side rooms, to test them. This is exactly how every investigation starts. Description first, hypothesis second, analysis third. Every population must be defined by animal, place, and time. Without all three, your rates don't have a valid denominator. Descriptive epidemiology answers who, where, and when, using epidemic curves, maps, and stratified counts. It generates hypotheses, but doesn't test them. Summary statistics should match data distribution, mean and standard deviation for normal data, median and interquartile range for skewed or ordinal data, and descriptive patterns, the what, always come before the analytical question of why. In the next talk, we move into the biology of how disease spreads, natural history, the epidemiological triad, chain of infection, and modes of transmission, the conceptual foundation for understanding why diseases spread the way they do in populations. Pause the video and try your hand at answering the questions in this scenario. Then we'll work through the answers together. Question 1. Population definition. Animal. Horses, all ages, all breeds, all management types, residing in the county. For analytical purposes, you might narrow to adult horses if the clinical pattern suggests age-specific risk, but start broad. Place, the rural county served by this veterinary practice, the geographic unit from which cases are drawn, and within which the denominator, approximately 15,000 horses, is defined. Time, March of the investigation year, or more precisely, the period from the date of the February flood to the date the investigation is closed, which defines the epidemiological window. A complete population definition, all horses residing in county name during March year following the February flood event. Question 2, crude attack rate. Attack rate equal cases divided by population at risk equals 34 divided by 15,000 equals 0.00227 equals 0.23% or 2.3 cases per 1,000 horses. This is a low attack rate, which is actually informative. It suggests either limited exposure, high background immunity, or both. EEE is a vector-borne disease with typically low attack rates in equine populations even during outbreak conditions. Question 3. Person, place, time patterns, and hypotheses. Animal, who? Adult horses disproportionately affected. Mean age 9.2 years. All affected animals unvaccinated for EEE. Hypotheses 1. Age-related susceptibility or immune status. 2. Vaccine status is a strong risk factor. Unvaccinated animals are selectively affected. 3. Adult horses may have different exposure patterns, turnout, pasture access than younger or housed horses. Place, where? 6 of 8 farms, 75% within 5 kilometers of the river corridor that flooded in February. Geographic clustering near the river strongly implicates a location-specific exposure. Hypotheses. 1. Flooding created standing water, ideal Aedes and Culiceta mosquito breeding habitat, increased vector density near the river. 2. River corridor wildlife, birds as reservoir hosts, concentrated near flood-affected areas. 3. Farms farther from the river had lower vector exposure. Time when? March. Onset following February flooding. The timing, approximately 2 to 4 weeks after flooding, is consistent with the time needed for mosquito populations to establish and reach infectious densities following habitat creation by flooding. Hypotheses. 1. Flooding created the conditions for EEE vector amplification. 2. The epidemic peak timing should correlate with peak vector density. Question 4. Descriptive statistic choice. Mean age of 9.2 years with standard deviation of 3.1 was reported. Was this the right choice? It depends on the distribution of age at onset. For a roughly normal distribution of ages in adult horses, mean plus or minus standard deviation is appropriate. However, age distributions in outbreak investigations are often right skewed. Without seeing the actual distribution, the choice is defensible possible, but should be confirmed by checking whether the distribution is approximately symmetric. Additional statistic to report alongside. The range, youngest and oldest affected animal, is particularly useful in outbreak investigation to establish whether very young or very old animals were disproportionately affected. The median should also be reported if the distribution shows any skewness, and reporting the proportion of affected horses by age group would be more informative than a single mean for understanding age-specific attack rates.